Today's problem is number of binary search trees from array. Difficulty is hard. Accuracy. Accuracy is really high for a hard problem. I think because what makes the problem hard is that there is a formula for the number of binary search trees that you can make from any given number of elements. You know, that could be in an array or, you know, any collection of elements. And if you know what that formula is, then it's not so hard. If you don't know what it is, and you get this question, yeah, you're probably going to have a tough interview. But we'll get to that in a second. Here's the problem. You are given an integer array, ARR, containing distinct elements. Your task is to return an array where the ith element denotes the number of unique binary search trees formed when ARR at I is chosen as the root. So here's an example. Let's see. So the array 2, 1, 3, what if we chose 2 as the root? Okay, so that is this example here in the center. There's only one possibility. You have to put the 1 on the left, you have to put the 3 on the right. So 1 is the first element in the output. What if we chose 1 as the root of the tree? Well, in that case, we can't put any numbers in the left subtree. They have to be in the right subtree, but there's two ways to make the right subtree. So output for 1 as the root is 2, and 3, let's see, 3, with 3 as the root, well, it's like 1, but, you know, in reverse. For 3, we can't put any elements in the right subtree. Everything has to be in the left subtree, but there's two ways to do that, so the answer is 2. All right. Number of binary search trees that you can make from some number of numbers is the Catalan number for the number of numbers. Now our number of numbers here is 3. Let's see. Well, here's the formula. There's different expressions for Catalan numbers. This is the one that I can remember. It's 2n factorial over n plus 1 factorial times n factorial. For example, in our case, n is 3, so on the top there we're going to have 6 factorial. On the bottom we'll have 4 factorial times 3 factorial. Now if we take this out, then really what we have on the top is we're taking 4 factorial off the top and the bottom, and then on the top now all that's left is 6 times 5. Now 3 factorial is 3 times 2, which is 6, so that cancels out, and what we have left is 5. So with 3 numbers we can make 5 binary search trees, which is correct. You can see we got 2, 1, and 2. All right. Now that unfortunately is not the question that we've been asked, but you know, we can sort of simplify it into that question. We've got a method here to pre-compute Catalan numbers, okay, and that makes sense because the array size only goes up to 6. So it really doesn't make sense to recompute the numbers over and over again if there's like 1,000 test cases or something. Oh, wait a minute. Why would there be 1,000? Well, I guess you could have the numbers in different order. So we're pre-computing the Catalan numbers. We're doing that with a dynamic programming solution. Because of the factorials, factorial is a good example of an algorithm that you can do it recursively, but it's not as efficient as if you were to do it with dynamic programming, because if you do it with dynamic programming, then you avoid the overlapping subproblems problem. Okay, so this is just bottom-up dynamic programming, and we're going to compute Catalan numbers up to whatever n is, the size of the array. All right, so let's take a look at that. N is our array length. We're going to look at this example here. It's 3. Let me scoot this over so everything is visible. Okay, sorted array. We are going to make a copy of the input array and sort it. So it would be 1, 2, and 3. Catalan numbers. We're going to call this method, and it's going to return an array of the Catalan numbers from 0 to 6. Actually, let me write those down. I'm not going to write it up to 6 because we only need it up to 3. But for 0, it's 1. For 1, it's also 1. For 2, it's 2. For 3, it is 5. So that's really all we need there. This is the result list that we're going to return, and then we can go into the algorithm. Let me scroll this up a little bit. All right. So actually we have 2 arrays. We have the initial array, which is 2, 1, and 3, and then we have the sorted array, which is 1, 2, and 3. Okay. And then over here we'll keep the list of that we want to return. So I is going to go from 0 to n, starts out at 0. We want to find the current element in the sorted array. So that tells us if we can find it in the sorted array, then we know how many elements will be in its left subtree and how many elements will be in its right subtree. So J, which also starts out at 0, so we can compare those. 0 and 0, they don't match. So let's increment J. What about, let's see, 0, I is the array. What about 2 and 2? Yes, that matches. So J is 1, and root index is J, which is 1. So if we come down here, left nodes equals root index, left index is, left nodes is 1. Right nodes is 3, minus 1, which is also 1. So what we're talking about here is, what if 2 is the root of the binary subtree? Then how many nodes is it going to have in its left subtree? How many nodes is it going to have in its right subtree? And the answer in both cases is 1. So we can look up the Catalan number for 1, which is here. This is 0 indexed. So 1 is 1. And we take 1 times 1 and add it to the result array. Okay. Back up to the for loop. I is now 1. So we're looking at the element of the original array at index 1, and that is 1. All right, we'll go down here. I should probably just erase that and start over and say J will start at 0. So the element at index I in the original array, 1, and index 0 in the sorted array. Now those do match. So J in this case is 0. The root index is 0. the left nodes is 0, and right nodes is 3 minus 1 minus 0, which is 2. So what if 1 is the root of the binary tree? Well, I scooted it out of the frame. I guess I could scoot it back. But if 1 is the root, then there is no left subtree. There's no left subtree. So you can see that over here. Everything is in the right subtree. So what we need is the Catalan number for 2. And the Catalan number for 2 is 2. It's right here. 2. All right. So result, add, multiply 1 times 2 is 2, and add it to result. It's 2. Okay. Start over again here. The for loop, I goes to 2. Now, we can jump ahead a little bit. I mean, 2, that's 3. So in order to match that in the sorted array, J is going to have to be 2 because that's where the 3 is. So root index is 2. Left nodes equals the root index, which is 2. And right nodes is 3 minus 1 minus 2, which is 0. Again, it's the same as 1, but in reverse. So there will be 2 nodes in the left subtree. That would be these 2 trees here. There would be 0 nodes in the right subtree. So Catalan at 2 is 2. Catalan at 0 is 1. Multiply them, we get 2. And we put 2 here. All right. So that's it. The secret to this binary search tree is formed from some collection of numbers. In this case, they're in an array, but they don't have to be in an array. You just need some collection of n numbers. And the number of binary search trees that you can make from that is the Catalan number for n. Okay. And let's see. I think that's it. I think we can go ahead and try to run it. Take all of those off. And hang on, move this over. Scoot that back a little bit. Let me do a quick sanity check on the compile here. Actually, I think I may have run this before. All right, submit. Okay. Oh, I didn't run it before. All right, that's it. Please go ahead and like the video. Subscribe. You can subscribe to the channel. You will get notified of problems of the day as they happen. And that's it. We'll see you next time.